we move forward with the following presentation. It will be presented by Josep Manuel Fàbrega from CTTC.
Now?
Yeah.
Now can you hear me? Yeah. Okay. Si me puedes sacar una foto, sí. Es que si no, no lo puedo justificar. Sí, vale. Okay, so let's see. Okay. Okay, good morning, everybody. I'm Josep Fàbrega from CTTC, which is a telecom technology center based in Castelldefels, Barcelona. And today I am going to present here what we call, or what is we understand as a scalable spectrum-based transmission for future agile high-capacity metro fiber optic networks. Okay. So, and what does this mean? So, if we take a look at the fiber optic networks of today, we will see that basically we can see three different segments. Okay, one would be the access part, which is more attached to the end user and also has some services to mobile networks. Then comes what we call the metro-regional part, which is basically a traffic aggregation from this access part up to what we call the core transport part, which is the part that features larger capacity and also in which the nodes have certain computing capacity, like data centers and so on. Okay, so and you can see that the ranges range from 20 kilometers or below in the access segment up to more than 200 kilometers in the core transport network. Okay. Seeing this, we can infer some new challenges to come within the fiber optical networks. Okay. First, we foresee that there will be a shift towards a user-centric perspective. So people will connect to internet or to different other services, regardless of the technology, either using the mobile phone, either connected at their homes or whatever. Okay. And also, since there will be a vast number of different applications and they will need to be hosted somewhere, we foresee what we call a telecom computing convergence. This means that the same infrastructure is expected to be used not only for delivering communication to the end users, but also to communicating different data centers between themselves in order to interact and acquire a higher computing capacity. Okay. So in order to cope with all this, we foresee the main challenges, the main requirements that we have faced in the past years also, but with increased numbers. This means that we will need a higher connectivity, higher capacity, security, and all this has to come with a reduced cost power per bit. Okay. If we go for the main technological challenges, okay, I am not going to this list. You can find it here. You can find it here in this white paper. But what's for sure is that photonic technologies is the key part that is going to make this happen. Okay. So if we take into account these challenges, we will see that the network that I presented before is slightly changed. It will not change in terms of architecture, perhaps yes, but not a huge change. But what we see is that there will be a huge number of computing resources around the metro regional part, meaning that this part will suffer for deep changes and is one of the key aspects to deal with in the upcoming years. Okay? And precisely this is what we deal in the Passion project. Passion project is a Horizon 2020 project coordinated by Politecnico di Milano. Okay? It started in December 2017. Okay? And among the partners, I would like to highlight that there is also VLC Photonics from Spain. Okay? And we have partners worldwide, not only European, but also we are receiving in-kind contributions from Optic, Optic, and even NICT. Okay? Technically speaking, okay, and if we take a top-down approach, okay, within Passion, in the network, we rely deeply on what we call sliceable bandwidth and bitrate variable transceivers. This means that we have transceivers that can vary its bandwidth and bitrate, can be programmed, and this can be stacked into modules in order to work as a single virtual transceiver altogether. That's why we call it sliceable. Okay? And within the specificities of the Passion approach, we go for modular and scalable. So this means that each transceiver is composed of different equal modules, and it can be easily scaled up according to the network operator needs. Okay. On top of everything, we foresee to put there a software-defined network controller in order to take care of all the network operations, program and configure everything. Okay. So if we go a little bit down, we will see the network node. Here is just a generic diagram. Okay, but the main parts would be these modules here, which are the multicast switches, and this part here, which would be the photonic switch, in which ones are able to add or drop the traffic, while the other one is just taking care of what's dropped or added, or either passed through the node. Okay, this is a generic one. Since in Passion we foresee different levels of hierarchy in the network, we came up with two different node designs. One would be a much more simpler one, okay, which would be this one, okay, which in fact is just something for aggregate traffic and drop traffic. Okay, and some AWGs plus SOAs for switching. Okay. And another one, much complex and much according to the generic architecture, okay, would be this one, okay, and this would be featured on a higher level of hierarchy of nodes, okay, in which we have different add switch WSSs, here the photonic switching module, and here comes in and out the traffic from to the adjacent nodes. Okay, and here comes the traffic from the nodes that are, or goes the traffic from the nodes that are in a lower hierarchy. Okay, I'm not spending so much time on here. If you are able to attend Photonics West this year, this will be presented there. Okay, and if we go even down, we can go into the architecture for the transceivers themselves, which I think is probably much more interesting. Okay. In fact, the transceivers are based on VCSELs, and they are long wavelength VCSELs. They are foreseen to have 25 gigahertz, 20 gigahertz bandwidth, and are foreseen to be manufactured within 25 gigahertz grid. Okay, they will be directly modulated using OFDM, multi-carrier modulation, and we expect to have up to 50 gigabit per second per pixel per state of polarization. So this means that we will have submodules of up to 10 different pixels, and since each pixel will be featuring up to 50 gigabit per second, we will have up to 500 gigabit per second per submodule. Then this will go onto what we call a module, which is composed by 4 modules, and in this module we will go up to 2 terabyte per second, and then we can host up to 4 modules in what we call a super module, and this will enable up to 8 terabit per second per state of polarization. So if we go by polarization division multiplexing, this will feature 16 terabit per second, and including space division multiplexing, okay, for example, standard 7-core fiber, we can easily deliver at each interface 112 terabit per second. Okay. So this is just another aspect of this transceiver, which is the spectrum. So in the end, the pixels are fixed, are not tunable, these ones. Okay, and here you can see the spectrum that is hosted at each submodule. So, for example, there is one submodule, this one that features the red dot here, that will have this wavelength, this wavelength, this wavelength, this wavelength, this wavelength, and they are like 100 gigahertz apart of it, but then comes the other submodule within this module that will be tuned by 25 gigahertz, okay, and so on and so forth. So in the end, by using all the submodules hosted in a super module, we plan to cover the full C-band. Okay, so sorry. So in terms of system perspective, what we have is a standard OFDM DSP, okay, which is in charge of generating the suitable waveforms, okay, and it's mapping data onto an OFDM waveform. Then this signal is clipped. Then we have an up conversion, pre-emphasis, and conversion to the digital to analog domain. And then comes the electro-optic front end, which in this case is a VCSEL. Okay, and at the receiver part, what we have is just a coherent receiver that will be an integrated one. In fact, our partner Photonics is in charge of that. Okay, and after having this, after detecting coherently this signal, we go back to the digital domain and perform a whole lot of operations. First, we just orthogonalize and rescue and normalize the components in order to compensate the possible misalignments here. We compensate for the chromatic dispersion, we estimate frequency and deliver it to the local oscillator in order to efficiently track the received signal. Then we go for a low-pass filter and perform the square, because in the end we will go for an intensity modulation. Okay, and we are detecting coherently an intensity modulation. We perform the down conversion afterwards, synchronization, retiming, and finally the OFDM DSP in order to obtain the data again. Okay, so in terms of systems, we think that DSP is key for optimizing the performance of the system, because in fact using VCSEL is no joke here. So it's really hard, because it's not as stable as we would desire. It has a quite large drift. It has a high line width. It has a non-negligible chirp. It has a lot of interesting things that we like to work with, which is low cost and, in this case, enhanced bandwidth, but it comes with a price. In this case, so what we did and what we recently did was to take 10 gigahertz VCSEL, which is not the final one that will be implemented in Passion. Okay, and we made several experiments in order to maximize the capacity using OFDM bit and power loading. So this means that we are adaptively modulating the signal in order to maximize the capacity according to the links established. And we made first a back-to-back characterization and optimization, and then we went for a network emulation environment. Okay, this is just a brief of results of the optimization, just a sample of them. We optimized the bandwidth of the low-pass filter at the receiver. We optimized the wavelength difference between local oscillator and the received signal, and also we optimized the orthogonality, the phase skew of the obtained components. So we can see that, for example, the phase skew poses almost no problems, because within plus minus 10 degrees we can have only a penalty of few gigabit, of less than 2 gigabit per second in terms of capacity. Okay, for a wavelength deviation, yes, the penalty is quite large. If we move a little bit down or up the optimal wavelength, and for the low-pass filter bandwidth, okay, it's just a matter of finding the optimum, but it's not so critical as here. Okay. So we wanted to compare this, because in the end what we provide is just another new technology, and we want to prove that it has some clear benefits with respect to the state of the art, which would be direct detection of intensity modulated signals. Okay, and for several values of OSNR, we measured the capacity either in direct detection or using the coherent receiver, which is the Passion approach. Okay, also in back-to-back operation, and we can see that around this value here, at 25 dB OSNR, there is a kind of trade-off. So below 25 dB OSNR, the coherent receiver performs much better than direct detection, but surprisingly, beyond this point, the direct detection outperforms the coherent receiver. We think that this is because the first coherent receiver is made of discrete components, so and there are several mismatches that between components that we were not able to compensate at all, even with all these algorithms for skewing or orthogonalizing signals and so on and so forth. Okay, but what's the good part here is that thanks to coherent reception, we can outperform the direct detection approach when going in bad conditions in terms of OSNR. Okay. Also, we made a preliminary network emulation, so that details will be presented in the upcoming OFC 2020. Sorry. And what we did was just to emulate one module and network node aggregator in the transmitter, okay, and then launch it to a 10-kilometer fiber, went through a couple of AWGs in order to emulate one of the nodes of lower hierarchy. Then we went through another 5 kilometers of fiber and went through a WSS plus a photonic switch in order to emulate a higher level hierarchy node. Afterwards went through 35 kilometers pool, then another higher level node with a couple of WSSs and a photonic switch, another 35 kilometer, another node. Then we went through a 25 kilometer multi-core fiber, okay, and then went through an attenuator in order to emulate the switching of the higher hierarchy node when performing pass-through. And after finally, we went through 50 kilometer fiber and went through WSS in order to emulate the part that is disaggregating traffic in a higher hierarchy node. Finally, we detected this signal, and within these conditions, we could come up with up to 160 kilometer path with these 5 intermediate nodes, and the preliminary results show a successful transmission beyond 20 gigabit per second per pixel, which is very good, taking into account the limits of the pixel bandwidth that we were using. And that would be it. In the end, what I wanted to present here is that future optical networks entail many challenges. Okay, that one, and probably the most important one, are dealing with metro-regional fiber optical networks. Okay, because we foresee that it's a segment that it will be rapidly transformed, including all these computing capacities that I told you before. Okay, and because of that, we expect it to be more agile, flexible, with increased capacity, but also it would be a very cost-sensitive segment. That's why in Passion we proposed our solution, which is the use of, in terms of transmission, which is the use of VCSEL modules in combination with integrated coherent reception, and we are working on that. We made preliminary experiments demonstrating its feasibility in different environments using even a limited prototype made with discrete components, but in order to be sure that from the systems perspective is something that is sound and able to work. So thank you very much, and I would welcome questions. Yeah.
Thank you, Josep, for your talk. Any question from the audience?
Great to see that you can do such long distances with VCSELs. I thought that one of the big challenges with the long wavelength VCSELs is also the reliability.
Sorry?
Reliability of the VCSEL?
Yeah.
Is that still an issue, or has that improved?
So what do you mean by reliability?
So just a long-term reliability, that the laser keeps working over, say, a long enough lifetime?
Yeah. Okay, yes, in the end, I'm not familiar with that. We expect it to be reliable enough. In fact, what we are doing is research, so this means that we are trying to demonstrate new concepts and so on, but we didn't do any specific tests on reliability here. But we foresee that why not? VCSELs could be a candidate, and the manufacturer that is involved in Passion is quite confident on that, so we rely on them.
Okay, thank you.
Okay, thank you.
Any other question?
Yeah, so I wanted to ask you, we are closer to the devices, the photonic integrated circuits, which is one of the key core technologies, but on the physical level of the network, similar to the multi-core fibers that you mentioned, 19 cores fibers. So you working at CTTC, you have a more of a system level perspective and closer to network operators, etc. What do you see are the adoption and the challenges of these innovative technologies like photonic integration or multi-core fibers for higher level system integrators?
Yeah, the point is that obviously integrators are reluctant to them. Not integrators, but network operators, because in the end they are the ones that are paying all the stuff, no? All the hardware. And they are the end users of that. So, and they want to maximize the rent. No, yes, they want to use as much as possible what they already have deployed there. So in terms of multi-core fiber, they are very, very reluctant to adapt it. But come on, if you need more capacity, in the end, you will have to pay for it. So I think it will be slowly adopted. But it is something that is like when we were many years ago talking between ADSL and FTTH. Now nobody can survive without fiber at home, right? But if you go back 10 years ago, okay, come on, fiber, no? What's this? No? And that's because operators were about to take advantage of all the copper lines that they had already deployed, and they were very reluctant to deploy a new media there and invest on new things. But in the end, it is something that you need to do in order to provide new services that will give an added value to your customers. So, in summary, it will come, but it will not be easy.
Thank you.
Okay.
Thank you, Josep, and again for your presentation.